Okay, so just to warm up on graphing, if I'm working with linear equations, I can graph each one, figure out where they intersect, and that will be my solution. All right, and then this one, this is the same problem, just a little clearer, straighter lines. We can see if I were to graph each of those in Desmos or somewhere, I can see exactly where they cross. So now we're going to start talking about graphing and solving quadratic systems. So the first one, y equals negative x squared plus 2x plus 5, is a quadratic. And then the second one is just a linear, y equals x plus 3. Y equals x plus 3, that's pretty straightforward. That has a y-intercept here at 3. X, the coefficient on x is 1, so my slope is just 1. So up 1 over 1, up 1 over 1. It's going to look like this. Missed. Try that again. There we go. That's a little better. Okay, so that's my line, y equals x plus 3. Now the quadratic, I need to be more deliberate now when I graph my quadratic because I'm looking at specific points where this is crossing at. So first off, do I know my intercepts on this one? My y-intercept. So looking at the top, negative x squared plus 2x plus 5. What is the y-intercept? 5. Okay, so I know it's going to cross right here. Is this one opening up or is it opening down? Down. I know it's open down from that negative. So let's actually find the vertex for this quadratic. So my vertex again, the x coordinate is that negative b over 2a. So in this case, it's negative 2 all over 2 times the negative 1. So negative 2 divided by negative 2, which ends up being positive 1. So the x coordinate of my vertex is here a positive 1. But I need to find the y coordinate. How do I find the y coordinate if I know the x value? Eric, what do you say? Okay, I'm going to put it right back here in this original. So y is negative of 1 squared plus 2 times 1 plus 5. Be very careful when you have that negative out front of your x squared. I strongly encourage to use parentheses because this is going to become now order of operations. I do 1 squared and then I do multiplication. So 1 squared times a negative 1. So I end up with negative 1. So if you didn't put parentheses there, you could easily make the mistake and say, well, that should be a positive 1 when it's not. 1 squared is 1, but then we have to bring in that negative, so it becomes negative 1. Plus 2 plus 5. Okay, so 2 plus 5 is 7, minus 1 gets me 6. So my vertex is here at 1, 6. So I have here another point right here at 1, 6. Also, I know with my vertex, that creates a vertical line for my axis of symmetry. So let's make a quick T-chart to stay organized here. I know my vertex is here at 1, 6. I also know the point 0, 5. The point 2 is going to be reflected over. It's going to be right here. So 2, 5, I know from symmetry that 2, 5 will be another point. Let's choose another one. Let's say if we were to look at negative 1. If I chose negative 1, I want to see where that one is lying on my graph. Well, if I chose negative 1, I got to go through my process again to find the y value. So a negative of negative 1 squared plus 2 times negative 1 plus 5. Now again, negative of negative 1 squared is going to leave me with negative 1 again. But now I have minus 2 plus 5. So 5 minus 2 would get me at 3, minus another 1 would get me at 2. So negative 1, 2 is another point, but because of symmetry, I can say 3, 2 is also a point. So now I have my parabola. Looks like this, comes back down, and I can see my solutions are going to occur here. I'm going to have a solution here, and I'm going to have a solution there. I actually have two solutions to this one, not just one. It's crossing. Those two graphs are crossing in two separate spots. So my solution would be negative 1, comma 2, and also 2, comma 5. Those would be the two solutions. Okay, and I'm writing those out as a coordinates, but what it's actually saying, the x values, is if I have a negative 1 or I have a positive 2, will get me to the same spots. And so this is graphing quadratic systems. Again, not much different than linear systems. We simply are graphing each one, figuring out where they intersect. Strongly encourage you to make those 2-column charts. I'm not seeing enough 2-column charts on tests, and that's where we get mixed up and we don't make accurate graphs. Use that idea of symmetry on the vertex, any quadratic. Figure out what the vertex is first, and then you can just start working out from that vertex. All right. All right, so going back to looking at linear systems. So when we were working with linear systems, we could graph it, figure out where they intersect, but if it does not intersect at a nice spot, a nice corner of our grid, we had to look at another option. What was another option we had, Brixton? Substitution. Okay, so substitution says if I had some function that was y equals 2x plus 5, and another one that I said y equals 3x minus 7, since they are both equaling y, I can rewrite this as 2x plus 5 equals 3x minus 7. I can set them equal to each other and simply solve for x. We can do the same thing with quadratics. We can solve quadratics using substitution. So now I have y equals negative x squared minus x plus 6, and also y equals x plus 3. So if I wanted to solve this using substitution, I'm going to set these equal to each other. So x plus 3 equals negative x squared minus x plus 6. All right, I'm trying to solve for x. Let's go ahead and put all my x's on one side. And so let's subtract x from here, and let's actually subtract 3 from here as well. So we can only subtract like terms. We can only combine like terms. And so now I have 0 on the left, negative x squared minus 2x plus 3. And equaling 0 now opens up a whole bunch of ways now that we can solve. So we have a quadratic. The last couple weeks we've been talking about solving quadratics. What's a method that we could tackle here to solve this quadratic? What did you say, Grace? Quadratic formula. Okay, let's try the quadratic formula. And so quadratic formula says I'm going to have x equaling, I have it written up there on the board again, so negative b, so the opposite of b, so this one would be now a positive 2, plus or minus negative 2 squared minus 4 times my a value, which is negative 1. My c value is 3, all divided by 2 times negative 1. All right, let's do this discriminant first piece. Let's clean up what's under that radical symbol. So negative 2 squared is 4, minus 4 times negative 1. So negative 4 times negative 1 would be a positive 4, times 3 would be a positive 12. So under my square root symbol here, I actually have 16. all divided by -2. Square root of 16 is 4, so now this becomes 2 plus or minus 4 divided by -2. Again, this is all, we're still solving for x. I just have numbers I'm working with, so I can keep going with this. So I can split this up. I can say, well, it's 2 plus 4 divided by -2, but also 2 minus 4 divided by -2. So this is 6 divided by -2, which is -3. And this is going to be 2 minus 4 would be a -2 divided by -2 to get a positive 1. All right, so quadratic formula works for any quadratic. As long as we have it set up as equal to 0, we can use the quadratic formula. And my two solutions, x is -3 and x is 1. I could have also done this with factoring. Okay, if I brought a negative out, I would end up with x squared plus 2x minus 3. And so this would be two numbers multiplied to get -3 that add up to be 2. Okay, can we think of two numbers that I can multiply to get -3 that add up to be 2? Inez? 3 and -1. And so I have a negative of x plus 3 and x minus 1. The negative on the outside here all the way to the left doesn't really mean anything. I mean, it's good, but it's not helping me find the solutions. So from this, again, we're setting this all equal to 0. X would be a -3 and x would be a positive 1. So for this problem, we could have used factoring as well as the quadratic formula. But you're limited on factoring. It has to be factorable. This one, fortunately, was factorable. But if you just want one go-to that you use every time and you don't try to bring in extra things, quadratic formula will work every single time. Okay? But sometimes factoring, you can see we did factoring in 2 steps, essentially. Quadratic formula took a few more steps, still got to the same answer. Do what you're most comfortable with. Okay? There's no right way or wrong way. This one we could use factoring, but if it was not factorable, we would have had to have used quadratic formula anyway. Okay, you do this one. -x squared minus x plus 12, positive x squared plus 7x plus 12. Okay, solve this one using substitution. So from this step, once we get everything, we set them equal to each other. We can move all the x's to one side and set it equal to 0. This one, is there a greatest common factor of 2x squared plus 8x? What can we factor out, Inez? 2x. And so this becomes x plus 4. So this one we didn't necessarily have to use the quadratic formula on either. This one is factoring, but not the factoring that we think of with a cross. This factoring is the greatest common factor. So I'm trying to make this equal 0 and this equal 0. Because if either one of them is 0, when I multiply them, I get 0 as an output. And so the only solution would be that x is 0 and also x is -4. So what this is saying, if I put in my equations over here, if I put in a 0 in the top and a 0 on the bottom, I'll get the same answer. If I put in -4 on the top and -4 on the bottom, I'll get the same answer. But those are the only numbers that will work. If I put in, say, 5, they will not be the same top and bottom. Out of all numbers possible, only 0 and -4 would work. It would fail if I used any other number. Okay, last one that we're going to work on for today. Solve the quadratic system of inequalities. So this one we're going to have a little bit of work to do with this one. But you just have to take your time, make sure you're attending to precision, staying organized, and we can do this one. Solving inequalities now, we bring in the dashed lines, we bring in the solid lines, do not forget those, and we bring in the shading. Okay, so the shading is the actual solution. So now it's not going to be only where they cross, we're looking at that shared shaded area when we do our shading. So we can do shading with parabolas too, not just with straight lines. So this one we have two quadratics that we're working with. So let's just look at the first one. Negative x squared minus 10x minus 1. So what's the first point I know right away simply looking at that quadratic? What's one point I know just looking at that quadratic exactly what point it's going to be? Ben, what do you say? 0, negative 1. So my y-intercept is right here. So the point 0, negative 1 is going to be one that we're working with. So over 0, down negative 1 is a point that we'll have. Okay, let's find the vertex of this parabola. So the vertex again is going to be found from that negative b over 2a, and you'll need to know this for tomorrow. So if you can't remember negative b over 2a, write this down and study it. So find the vertex. So a negative b over 2a. So this would be now a positive 10, all divided by 2 times negative 1. So 10 divided by negative 2, which would be a negative 5. So I know negative 5 is going to be a point, an x value. If I want to find the y value, I'm going to just put in negative 5. So negative of negative 5. So be very careful. If it's a negative x squared, use parentheses to stay organized. Negative of negative 5 squared minus 10 times negative 5 minus 1. Negative 5 squared is 25, but we have this negative, so it's a negative 25. Negative 10 times negative 5 would be a positive 50 minus 1. Negative 25 plus 50 brings it back down to 25 minus 1 is 24. So negative 5, 24 is going to be a point that I'm working with. So I know that is my vertex. Negative 5, positive 24 is the vertex. Based on the vertex, I know I have symmetry. So if I have the point 0, negative 1, so 0 to negative 5, I also know at negative 10, we'll have a y-coordinate of negative 1. Because negative 5 is halfway between 0 and 10. So at negative 10, I'll also be here at negative 1. All right. Is this going to be a solid or a dashed line? This one is dashed. Okay. Y values cannot be the same as my line. The one below it, y is greater than or equal to, that bar on the or equal to piece reminds me that it's a solid line. So this is going to be a parabola that goes up here, curves back down, and looks like that. Now for the shading on this parabola that I've just drawn. So y value is less than my line. So if I chose any point on here, I'm going to be shading below my line. So I'm just going to draw a little arrow just to remind myself that I'm actually shading below this line. I don't want to do any shading yet because I don't want to shade the solution set, that area, but I'm going to be shading below this line. Let's look at now the second equation, x squared minus 2. All right, I know my y-intercept's here at negative 2. And so I have 0, negative 2 as a coordinate. This one is actually going to be the vertex as well, because x squared minus 2, I could have written that as x minus 0 squared minus 2. So that is the vertex. So let's just start working out from that. If I chose, say, a negative 2, If I put that back into my function, negative 2 squared minus 2 is going to be 4 minus 2 to get to. So negative 2, 2 is also a point. And a positive 2, 2 would be a point due to symmetry, because it's going right through my vertex. And I could keep going. I could say negative 5. Negative 5 squared minus 2. It'd be a 25 minus 2 to get 23. So at negative 5, I'm up here at 23, just below it. And then also at positive 5, I'm going to be up here at 23. And then we decide this one is a solid line. So I'm going to keep this one solid when I graph my parabola. Go up like that. And now my shading, I want y values greater than my line. And so I'm going to be shading up from this line. My solution set then will occur in between these two. So it's below the blue line, but it's above the red line. So it's all of this in here. All right, and mine's getting kind of messy. So here's a little bit better, a little bit cleaner example of exactly what it looks like. Using Desmos, I graphed these, but you can see that middle strip is darker than the rest of it. That is the solution. And on the test, I only want you shading in that solution area. Don't shade everything like this. Simply shade in that solution section. So as long as we're comfortable graphing parabolas, inequalities are not any more difficult. Only thing it brings in is dash versus solid lines, and we have to do our shading properly. All right, so we can solve quadratic systems using graphs. We can solve quadratic systems using substitution. And then we can also solve inequalities using graphs by our shading. Okay, that's it. If you want to go ahead and look at these problems, 262, 8, 9, 14, 15, 16. So there's 6 problems that you have to work on. Have those ready to go for tomorrow, and then we will take a few questions and have our test.